In the previous lesson, we looked at an object moving in a circle. And in particular, we looked at how the velocity of that object changed and what it looked like, and also the acceleration of that object. One of the diagrams we did is we said, imagine you are above, sort of hovering above, looking down at this object that's moving in a horizontal circle. You'd see its path look something like this. And on top of that path, we drew what the velocity and the acceleration would be like at different points. And that gave us a drawing that looked like this. Okay, so we have the velocity, which is always tangent to the circle, which means sort of like parallel. Or another way to describe it is the velocity is always perpendicular to the radius. And we have the centripetal acceleration, which is always towards the center of the circle. The next thing we looked at was how we might be able to calculate the speed and the magnitude of the acceleration for this type of motion. And we came up with this. All right, so the speed was just the circumference of the circle, 2 pi r, divided by the time it took to go around the circle once, the period. And the acceleration, or the magnitude of the acceleration, was that same speed squared, divided by the radius of the circle. And it turned out that there was another way we could write that that meant the same thing, but just used slightly different variables. So now remember that when an object is accelerating, it must feel a net force. So because I have acceleration the whole time I'm going around the circle, there must be a net force on me the whole time that I'm going around that circle. And because F equals ma, that force has to be in the same direction as the acceleration, which is towards the center. So this force is known as the centripetal force. It's not now one thing I want you to realize here is it's not a new type of force in the same way that friction is a type of force, or tension is a type of force, or gravity is a type of force. All of those forces have sources. Gravity comes from, Earth's mass. Tension comes from a rope. Friction comes from another surface that you're sliding against. So centripetal force isn't like a new force with a new source. Any force we already have talked about could be a centripetal force, as long as it points towards the center of an object, of a circle, that is the path of an object in circular motion. So any force can be a centripetal force. It's kind of like the word net force. Any force can be the net force. Any force can be a centripetal force. Here's some examples of different centripetal forces. So if an object is twirled in a circle at the end of a string, which is the situation we looked at in the previous lesson, the centripetal force, the force that's pulling the object towards the center of the circle, comes from the tension in the string. If a car goes around a corner on a highway, right? The car is moving in a circular path. So there's an acceleration towards the center of that circle. And this one's maybe not super obvious, but what I'd like you to think about is if the cars are going in a circle around a corner, and then the car suddenly hits a patch of ice, what will it do? Well, it won't keep going around the corner. It won't continue to move in that circular pattern. So that kind of helps you maybe shed some light on this. What happens when we hit ice? Well, we lose our grip. We have no more friction. So if getting rid of friction stops me from going around a corner, accelerating towards the center, then that must mean that having friction is what causes me to do that. So the centripetal force when a car goes around a corner is provided by friction. The grip between the car's tires and the ground. If you lose that grip, you can't go around the corner. And a more obvious example here is the moon orbiting the Earth. So the moon will travel in a circular path around the Earth, meaning it is accelerating towards the center of that circle. So there's a force towards the center of that circle. And what's the force that pulls the moon towards the Earth at the center of its path? Well, in that case, the force would be gravity. So there are cases where tension is a centripetal force. There are cases where friction is a centripetal force. And there are cases where gravity is a centripetal force. There are other examples too, but I'm just trying to highlight the fact that the centripetal force is not a new type of force. It can come from any force that we may already have talked about. Okay, so let's tackle a couple of examples here. A plane makes a complete circle with a radius of 3,622 meters, and it does this in 2.1 minutes. What is the speed of the plane? Okay, so here we're being asked for the speed of an object that's in uniform circular motion. Well, we said that for an object in uniform circular motion, the formula for speed was this, 2 pi r over t. So let's see if we can use that here. Speed is 2 pi r over the period. Okay, well, 2 is a number, pi is a number, r is the radius of the circle the object is traveling in. I know that here. And t is the period, the time it takes to go once around. And that is here. It's a little annoying that my t is in minutes. That's not metric base units. So the first thing I'm probably going to have to do is adjust that. It turns out that 2.1 minutes, 2 minutes is 120 seconds. 0.1 minutes is 6 seconds. So this is 126 seconds if I convert it to metric base units. So 2 pi r is 3,622. That's metric base units. And t is 126. If I round this to 3 sig figs, I get 181 meters per second. Okay, that was kind of our simplest formula, and it was a simple scenario. Let's look at something a little more complicated. A car is traveling at 14 meters per second. It goes around an unbanked curve in the road that has a radius of 96 meters. What's its centripetal acceleration? Okay, well, our formula for centripetal acceleration was this. We have two options, one with a v in it and one with a t in it. So we're going to ask ourselves, which one would be more easy to use in this scenario? The one with the v or the one with the t? Well, I'm given the v, and I'm not given any information about t, the period. So I might as well use the formula that uses the things I know. So crunching those numbers gives me 2.0417, or rounding to 3 sig figs, 2.04 meters per second squared. That is the magnitude of my centripetal acceleration. Now, the direction, as always, because it's a centripetal acceleration, will be towards the center. Okay, part B is where we get a little more interesting. We want to know about the coefficient of friction between the road and the car's tires. So this means we want to know something about forces. And so far, we don't have any forces in any of our formulas. We know about the speed of this car. We know about the acceleration of this car. Those are sort of kinematics things. And now we're being asked about forces. Well, what formula links the world of forces with the world of kinematics? That would be Newton's second law, F equals ma. And indeed, that's what we're going to use. But first, I think we should do a bit of a free body diagram. So here's my car. This is sort of a back view of the car. There's one tire. There's another tire. It's got like a license plate. Maybe a couple of brake lights. Pretty square looking car, but that's my car nonetheless. So it's driving into the page. It's driving away from us. And it's turning to the left in a big circle. So you can imagine if we let this car go long enough, it would go into the page, turn left, turn left, turn left, turn left, turn left, and turn all the way around 180 and be coming out of the page sort of somewhere over here. So what I'm going to do, because I think it's always sort of good practice, is I'm going to draw a star to show where the center of the circle is. So the car is going into the page over here. It would go behind that star and then come out of the page, over here somewhere. All right, so forces. Let's switch up the colors a bit. Forces acting on this car. I have Fg going down. I've got a normal force acting up on the bottom of the car's tires. And I've got friction. And friction is pushing me towards the center of the circle. We talked about this a little bit last lesson. It seems a bit odd because we're used to friction sort of opposing motion. And it does always oppose motion. But we kind of want to think, well, the car's going forward, so wouldn't friction be backwards? Well, friction occurs when things are sliding or trying to slide. There's no sliding going on forwards, backwards. The car's wheels are just rolling. Where we need to worry about sliding happening is if this car takes the corner too fast, or if the car hits a patch of ice and suddenly is no longer able to stay on that circular path and ends up just gliding sort of straight ahead, according to Newton's first law. So the thing that's pushing the car towards the center of the circle, that's making the car turn, is the grip between the tires and the road, is the friction. And that's this guy here. Force of friction. So there's my free body diagram. I've got normal and gravity. Those are the only forces in the y direction. They're going to cancel each other out because there's no acceleration in the y direction. The car is not hovering into the air or burrowing into the ground. And then I got one force in the x direction. It's friction. And it's going towards the center of the circle. So friction is my centripetal force. Okay, so back to F equals ma. Well, if I add up all the forces, like I said, normal and gravity are going to cancel. So the only thing left is force friction. And I'm going to say that it is positive. You might be thinking, well, why are we saying it's positive if it's going to the left? Well, I want to adopt a new convention for positive and negative that we'll use with circular motion. And that is that positive is towards the center of the circle. If we say right is positive and left is negative, then we have situations where the sign is always changing. Here V would be negative because it's left. Here's V would be positive because it's right. Maybe here you'd say it's positive because it's up, and here you'd say it's negative because it's down. And it would always be changing, sometimes positive, sometimes negative. That would be annoying. So we're just going to say towards the center is positive and away from the center is negative. So friction, because it's towards the center, is going to be a positive force. And the acceleration of the car, we also found, was that number, or rather this one. And it was also a centripetal acceleration, so it was towards the center as well. It was also a positive number. Okay, but I don't want to find friction. I want to find the coefficient of friction. In other words, I want to find mu. Now, what's happening between these cars' tires and the ground is hopefully these cars' tires are not slipping. You don't want this car to be skidding. If you're skidding in a corner, you're losing control. You're probably not going in a circle anymore. So we want there to be no slipping between the car's tires and the ground, which means we're looking at static friction, where friction is less than or equal to mu times force normal. Now the annoying thing here is this less than or equals to sign, because it's not super easy to do math and algebra with inequalities. It'd be better if that was an equal sign. And remember, friction only, the reason we have this inequality here is because friction is only as big as it needs to be. So if I take mu and multiply it by the normal force on this car, which are both fixed values, I'll get a number. But friction will probably be less than that number. Friction only goes as high as it has to. If friction only needs to be 1 Newton to keep this car going around the corner, it'll only be 1 Newton. If friction needs to be 10 Newtons to keep the car going around the corner, it'll be 10 Newtons. But the maximum value friction can go to is mu times that force normal. And when friction is equal to that number, we're just about to slip. Friction cannot go any higher. And if we try to make it go higher, the car will slip. So this inequality becomes an equality when we're on the verge of slipping. And that's exactly what we have in this problem. We want to know what the minimum coefficient of friction needed between the road and the car's tires is. We can have a really big coefficient of friction that's more than we need, in which case we're not worried about slipping. But if we want just the smallest coefficient of friction we can possibly have while still keeping this car on the road, that means we're kind of playing with fire here. We want to have just barely enough grip to keep making this corner. In other words, we're on the verge of slipping, and we can say friction is equal to mu times force normal. Okay. Thing here is, we don't know what the normal force is. And we don't know what the mass of the car is. But we know that Fg equals mg. And we already talked about how, in this case, the normal force and the force of gravity have to have the same magnitude. So that means force normal is the same as force gravity, which is mg. And now the m's can cancel out, and I can solve for mu. So if I take this and divide it by little g, which is 9.8, I get mu is 0.208. Okay. So how do we tackle this problem? We started by drawing a free body diagram. We labeled all the forces, and we made sure there was a force going towards the center of the circle. Whenever an object's in circular motion, there's a force towards the center. In this case, it was friction. It could have been something else. Then we used F equals ma. And for our A, we found it using our new formula for centripetal acceleration. And those are sort of the fundamental steps that you'll be using solving problems going forward on this topic. Now, one thing I just want to address before we leave this is something called centrifugal force. I've been using the word centripetal a lot. You've probably never heard the word centripetal before, but you might have heard the word centrifugal. And this is problematic. Centripetal means center seeking, or towards the center. Centrifugal means center fleeing, or away from the center. So the reason we haven't been using the word centrifugal very much is because there's not a lot of stuff in these situations that's going away from the center, right? Here, there were no forces going away from the center. In our diagram back on this first page, none of these velocities or accelerations are going away from the center. So why do people have this word centrifugal that they use so often when it doesn't really apply, it seems, to any of these situations? Well, centrifugal force is sometimes referred to as an apparent force. It appears to be a force. We feel like it's there, but it's not actually. So if you're in a situation where you are rotating, let's say you are a car and you're going around a corner, you're driving in a circle. And let's say you're driving in a circle for so long that driving in a circle just feels like normal to you. Everything in the car, sitting on the seats in the car, hanging from the ceiling in the car, attached to the dashboard in the car, just keeps going in a circle. And you kind of get this sense that things will just keep going in a circle forever, and that's what everything around you wants to do. It wants to keep going in a circle. But then let's say on the back seat of your car, the back bench, there's a ball. And as you speed up and take the corner harder and harder, the ball actually starts to roll towards the side of the car, towards the outside of the corner. If you're this car who's just used to everything going in a circle with you, you might look at that ball and think, that's really weird. That ball suddenly started to roll towards the outside of the car, towards the outside of the corner. You might think there must have been a force that pushed the ball towards the outside, and you would call that a centrifugal force. But that's because you were expecting the ball to go in a circle with you, which is not really fair. We know that things don't want to go in circles. They don't tend to go in circles. Newton's first law tells us that things tend to go in straight lines. And it's not that if that ball wants to kind of keep going straight and not do the circle with you, it's not that we need a force to stop the ball from doing a circle. It's that we need a force to make the ball do a circle. So it can be tempting to say, if you're moving in a circle, that that's the normal thing to do. And for an object to go straight and leave that circle, we would need a centrifugal force on it. But it turns out that we do not need a force to make an object go in a straight line. We only need a force to deflect an object from moving in a straight line. Straight lines is what things want to do. It's the object going in the circle, making the corner, that needs the force. So what we think of, if you're in this car and you see the ball roll across the seat, what we think of as a force pushing the ball towards the outside is really just the ball wanting to keep going in a straight line while the car underneath it continually turns a corner. So what is it that makes a ball want to keep going in a straight line, or any object for that matter? Inertia. So there's no such thing in the real world as a centrifugal force, just inertia. Things don't need to be pushed to not go in circles. Things automatically want to not go in circles because of inertia. But if you're traveling in a circle and you see something near you leave that circle, it can seem or feel like that object felt a force, even though it didn't. Okay, and so this example here of the backseat of the car is what I've been talking about. If you're riding in the middle of the backseat of a car and it's turning a corner, you will feel like you're being pushed to the outside of the corner by an invisible force. But there's nothing pushing you towards the outside of the corner. It's inertia. There is a force pushing you towards the inside of the car, but nothing towards the outside. So there is a force from the seat or from the belt on you, and they're pushing you towards the inside of the car, of the corner, making you stay with the car. There is no force towards the outside. However, you will seem like your body wants to go towards the outside because that's where inertia wants you to go, in a straight line. If your seatbelt breaks, you slide across the seat. You seem like you're accelerating towards the outside of the corner, but what is actually happening? You're moving in a straight line while the car underneath you is continuing to turn a corner. So centrifugal force is something that appears to be there to an observer who is moving in a circle. But to someone in an inertial reference frame, someone standing outside the car or the object moving in a circle, it's clear that there is no such thing as a centrifugal force. There's nothing pushing objects towards the outside of the circle, only the centripetal force pushing towards things towards the inside. Things may want to go towards the outside, but that's because of their inertia, not because of any